All right, so we are now starting the section 9-3 test review part of the chapter 9 test review document. So again, this problem is worth 2 bonus points if you turn it in by Monday, the first day of finals week. All right, so our problem statement says a study of iron deficiency among infants compared blood hemoglobin levels of a random sample, that's good, of infants who had been fed with standard infant formula to a random sample of infants who had been breastfed. Here are the results. So we have formula-fed infants and our breastfed infants, sample sizes, sample means, sample standard deviations. Okay, so it doesn't appear that there's any connection between the two samples, which is good, right? There's no matched pairs or anything. So this is going to be our strategy for a difference in two means with independent samples. So it says let mu sub f equal the population, right, goes with mu, mean blood hemoglobin levels. So mean is average, the population average of the blood hemoglobin levels for formula-fed infants. Makes sense, F for formula. And mu sub B equal the population mean blood hemoglobin levels for breastfed infants. Again, makes sense, B for breastfed. All right, so assume the population blood hemoglobin levels for both groups are normally distributed. Okay, that's interesting. So is there convincing evidence that on average, blood hemoglobin levels for formula-fed infants are lower than blood hemoglobin levels for breastfed infants at the alpha equals 0.05 significance level? All right, again, convincing evidence, significance level, that tells us we're doing a hypothesis test. So let's get started with our state. First, we're going to state the parameter. So they listed formula-fed before breastfed, so I'm going to call my difference, right? If I want one to be lower than the other, I'm going to consider the difference between them. The difference between mu sub f minus mu sub b, okay? So that is going to be the true difference, not the true mean difference, but the true difference in mean blood hemoglobin levels. And I'm going to subtract with formula-fed minus breastfed. Okay, so now I need to state my statistic. So let's see. I'm going to match mu sub f with x bar sub f. So that would be this one over here, right? My 12.4, that's the sample mean for formula-fed infants, minus replacing mu with x bar for b for breastfed. So it's the sample mean for breastfed infants. So let's plug those in. 12.4 minus 13.3. Okay, 12.4 minus 13.3, negative 0.9. All right, so my sample difference in means is negative 0.9. So I have some evidence that the formula-fed infants have lower levels than the breastfed infants, right? Lower than the breastfed. But I don't need to know if that's convincing evidence. And to do that, I'm going to do my hypothesis test. So alpha equals 0.05, that was stated. And then I need my hypotheses. So let's see, our null hypothesis is always an equality. It's always equal something. So I could just say mu sub f equals mu sub b, but I'm going to keep it in that difference form. Mu sub f minus mu sub b, that's my parameter, equals 0, right? If they are the same, then their difference would equal 0. My alternative hypothesis, last time it was just that the parameter was not equal to 0 because all the problem statement said was, are they different from each other? But this time they're thinking that the formula-fed are actually lower than the breastfed. So this tells me that I want to have a one-tailed test. And specifically, I want formula-fed to be less than breastfed. So when I subtract them, I'm going to get a negative value. So mu sub f minus mu sub b will be less than 0, right? Negatives are less than 0. Okay, so I've got my hypotheses going there. So now let's plan. All right, so again, this is a 2 sample because I have 2 independent samples. But this time, because it's for means, it's a t-test for mu sub f minus mu sub b. All right, let's check those conditions. So the first condition is the random condition. And it does say, I'm going to abbreviate here, that they're random samples, and I can tell that they are independent, right? There's no connection between the breastfed and the formula-fed infants. The second condition is the 10% condition. So let's check N1 is equal to what? 19, and N2 is equal to 23. We want to see if they are less than 1% of all formula-fed infants. Where within 2, we want to check that that's 1 or less than 1/10 of all breastfed infants. I think it's reasonable to assume that there are more than 194 formula-fed infants and more than 230 breastfed infants, so that condition is met. And then our third condition is the normal condition. And in this case, it says our populations are normally distributed. So I'm just going to write that. Populations are normal. This may be the first time that we've ever been able to check the normal condition off that way. Usually we have to check that our sample sizes are greater than or equal to 30, which in this case they wouldn't be, so it's a good thing that this is stated. Or we'd have to check the sample distributions, the actual data values, to check that they look fairly normal. And we don't have the sample data, we just have the descriptive statistics. So again, it's good that this was stated. Okay, so then we have the do step. And this time I'm not going to actually write down where we're going because this was given to us in our notes. And I think kind of with common sense, you can figure out where we need to go. So we're doing an analysis, we're doing a hypothesis test, and it is a 2-sample test for the difference in means. So let's find that in StatDisk. Oops, wrong button, sorry. All right, so I'm going to go, this is from last time, the confidence intervals and proportion of true samples. I'm going to go to analysis, hypothesis test, and I'm looking for a mean. I have more than one sample. I have 2 independent samples. They are not matched pairs, so I want mean 2 independent samples. And then I have the option to use summary statistics, or descriptive statistics is another word for that, or to use data. I don't have the individual data values. I have to use summary statistics. So let's get alternative hypothesis correct. We want the population mean 1 to be less than the population for mean 2. If you are kind of confused about this, rearrange this one, the alternative, add mu sub b to the other side. If I did that, I would have mu sub f is less than mu sub b, right? That's what I'm looking for, formula fed to be less than breastfed. So that is what I'm entering here as my alternative. My significance level is still 0.05. So let's get the sample size correct. For the first sample for formula fed, it's 19. The sample mean for the first one is 12.4. The sample standard deviation for the first one is 1.8. And then I don't know the population standard deviation, so I leave that blank. For breastfed infants, the sample size is 23, the sample mean is 13.3, and the sample standard deviation is 1.7. I got all the information from this table right here. Okay, so again, I don't know the population standard deviation, so I skip that. Over here in method of analysis, I don't change anything. I leave it as unequal variances. And then I click evaluate. All right, so I check up here that my alternative hypothesis matches what I wanted. I have my t-test statistic, and then my p-value. Again, it gives a corresponding confidence interval. Notice this is a one-sided test, so even though I had a significance level of 0.05, it gives me a 90% confidence interval. But I really am not interested in that right now. This is a hypothesis test. I want the p-value. So that's at 0.05325. All right, so used StatDisk. That is what you need to write to get a p-value equal to 0.05325. All right, so now I am ready to conclude. So I always start by comparing my p-value to the significance level. So since the p-value equal to 0.05325, it's just a little bit greater than alpha, but it is greater than alpha. So it's greater than alpha equal to 0.05. We fail to reject the null. Okay, that means we do not Whenever we fail to reject the null, we do not have evidence against it. So we do not have convincing evidence. Now I could say that the true difference in mean blood hemoglobin levels is not different. That's one way to put it. We also want to, or in this case, we want to try to match what the problem statement says. So we do not have convincing evidence that the blood hemoglobin levels for formula-fed infants are lower than those levels for breastfed infants. So that average blood hemoglobin levels for formula-fed infants are less than, I'm just going to say the levels instead of repeating that all out again. I think it makes sense. Are less than the levels for breastfed infants. We do not have evidence of that. If our p-value had been less than alpha, then we would reject the null and we would have evidence for this. Okay, so now we're going to go ahead and construct and interpret a 90% confidence interval. Notice alpha of 0.05 corresponds to this 90% confidence interval for the difference in the mean hemoglobins for formula-fed and breastfed infants. So I want you to take a look at the confidence interval we've got here. Negative 1.81778 to negative 0.01778. Let's see if that matches what we do when we actually run analysis, confidence intervals. Again, we're choosing mean for 2 independent samples because that's what we have. And plug in our information again. Remember, it told us to use a 90% confidence level, so we're changing to 0.09. Let's see, we had a sample size of 19, sample mean of 12.4, sample standard deviation of 1.8 for the first sample. Second sample was a sample size of 23, sample mean of 13.3, and a sample standard deviation of 1.7. Okay, again, we don't change anything down here. So evaluate and look at that confidence interval. It's exactly what was given to us before. Now, however, notice the p-value is literally twice what we got before. Our p-value is 0.05325. This is 0.10651. It's multiplied by 2. That's because whenever you run this confidence interval in StatDisk, it gives you the p-value for a 2-sided test. We didn't do a 2-sided test. We did a 1-sided test just for the first population being less than the second population. So please be careful to actually do the correct process in StatDisk. But it does give us the confidence interval we want. So negative, I'm going to round this time, negative 1.82. How's that? Oh, wait, I forgot, and I have a feeling you will too. There are a few things that we need to state and plan that were different from what they are in Part A. So I think we can say, I'm just going to put quotes this time from above from Part A, but with 90% confidence. Remember, I have to state my confidence level for a confidence interval, and I only had a significance level up here, so it's important to have a confidence level down here. My plan, again, the conditions are the same, but my test or my procedure name is different. This is a 2-sample T interval for mu sub f minus mu sub b. Okay. Now I'm ready to write down my confidence interval. So again, I used StatDisk, and I get an interval of negative 1.82, comma, let's see, it would be 0.02 if I rounded 2 decimal places again. 0.02. So again, I can tell 0 is in this interval. It's possible that they are the same, but they could be as different as 1.8 blood hemoglobin level. I don't know what the units are there, or a difference of 0.02, right? I cannot know for sure the true difference value. I just know that I can't rule out 0. Okay, so now I'm ready to conclude. We are 90% confident that the interval from from negative 1.82 to 0.02 captures the true difference in mean blood hemoglobin levels for formula-fed and breastfed infants. Okay, there we go. Our conclusion is done. It did not ask me in part B to make a statement about convincing evidence, so I don't have to go ahead and say the interval says we don't have convincing evidence that there is a difference. But if you are asked that, that's what you would say. Okay, in the next video, we will cover section 9-4.